Good morning, students. And today we'll be working on a very classic yet very famous algorithm. And even until today, I think in a lot of machine learning territory, random forest is one of the fans' favorite, right? So let's learn about random forest today. In fact, if you study the previous tutorial on backing, random forest is built upon the previous idea of backing, that is the idea of having a bootstrap data set across different tree. Then because each of the trees see different versions of the data set, you can guarantee that there's variances between each of the tree. Then based on that, the results will come slightly different. But because they are slightly different, that is good, right? It reduces the overfitting. But at the same time, when you take the average or the majority of the prediction, we hope that that would give us the best prediction result, right? But anyway, random forests are built upon that backing idea and add two more concepts to make this random forest idea. So the first is out-of-back evaluation. You will notice that each tree only see a subset of the data set. So that anything that is not inside the subset, we call this out-of-back. And and the idea is very simple, because each of the tree don't see this data. We can actually use them as a validation set for that particular tree. So that is one idea, out-of-back evaluation. And another idea is that, hey, bootstrap data set is very nice. We take the subset of a sample from the data set for each tree, but we can further increase the variance by selecting only a subset of features. For example, if we have n features, we can select only q features, right, from these features. So, based on a lot of research, people recommend that it should be something like, if n is like 25, then q should be 5, something like that, right, for classification trees. And for regression trees, it should be something like n divided by 3, roughly, right? So this is just based on research, but I don't think this is a big deal. I think the main idea is that, hey, if we just select randomly a subset of features, we can further increase the variance of the bootstrap data set. So these two ideas plus the backing create something called random forest. All right. So today, let us code this and see how random forest work, right? So let's start right now. So what we need to do is we're gonna do import right here, and we're gonna create a class, right? And here we're gonna have an init function, fit function. What else we should have? I think we should have the predict function, right? And then finally, we want something like model equal to, let's say, random forest, b equal to 5, bootstrap ratio equal to, let's say, 0.8. Last time we used 1 in our previous tutorial, and then we want to do something like model.fit xtrain, ytrain, and then y hat equal to model.predict xtest, and then finally, what do we want? We want to print classification, classification report, y test, y hat, right? So that is what we want to do, right? So let us try to work backward and try to see what do we need to do here. So firstly, what I want to do is import random and that. I'm not gonna use our decision tree. I'm gonna just use sklearn, so that things are easier, right? And of course, we're gonna use the SciPy again, so that we can do the majority, the average, the thing from the backing for the backing, and of course, sklearn.matrix import accuracy script. All right. And of course, we need, I'm not sure, did I import NumPy? Yes, I think I did, right? So I think that's it. And then let's start right away. So our class very surely is this name. So, and we need what we need. Well, we need the init function, right? And we are sure we need that. And for the fit, I think we need that. And then finally for the predict, we do that, right? Okay, great. So for the init function, I think we already defined that we need this B and bootstrap ratio. So let us make sure we have that. And okay, how about we don't have any default so that we make sure that the user specify that. And then I also want to add something called B with no replacement equal true. This is just for the backing, right? And we're going to say self.b equal to B and then self.bootstrap ratio equal to bootstrap ratio and self.with no replacement with no replacement and self.3 params equal to max depth 2 and max features square root. All right. And then the models decision tree classifier. And some people ask me, why do we need to put double star, right? Well, if you're inputting a dictionary as the argument, the function need to know that this is a dictionary. And the way you do that is putting a 2-star here. When I say dictionary, a lot of people use something called keyword arguments, and that is the same thing, right? If you put 1-star, it means this is a tuple, right? A tuple looks like this, right? Like hello, Jackie, something like that, right? Hamburger, French fries, something like that. This is a tuple, right? So it's start with a parenthesis and then with comma, right? So that is the idea. But anyway, here we're going to use 2-star here, and for in range B, and I think that's it, right? So here, notice that I'm putting here max features equal to square root, which already implement this for us. That is, it already randomly select square root number of features, right? For us. Yep. All right. And I think that should be. And let us do the. Okay, let's see what we should do first. So how about we do this prediction first, right? It's easier. So we know that this is x, right? And usually this x is basically x test. And we can do this predictions equal to np.zeros. Similarly, we have b prediction. We'll have b of the prediction, and we have that many of predictions, right? And then for I comma model and enumerate self.models y hat equal to model.predict x. Oops, sorry. And predictions I comma is that equal to y hat. And then what we want to do is we just want to return the one with the highest predictions. Okay, great. So that is that. Now let us look at the fit, right? For the fit is a little bit long, but if you follow my previous tutorial, then there should be no problem. All right. The only thing I add is probably the out of back evaluation. So let's do this quickly. So I have x and y, and you can assume this is x train, and for the x shape, and we have to say the sample size equal to n self.bootstrap ratio times the length of the x. and X samples, we put np.zeros, cell.b, sample size, n, and I think we can do the same for okay for y, but we don't really need this because y doesn't have the features. So that is y. How about we put everything here in one line so we know that this is related to shapes. Okay. Now of course we need something a placeholder. We put the OOB. So we're gonna put a list, and similarly we're gonna also do the same for that. And now we can do this for I in range cell.b. What do we do? Well, we need to set who are the, we need to keep track who are the OOB and the indexes. Now what do we do? For J in range sample size, we're gonna randomly pick, we're gonna randomly pick anything in the range of M. And if self dot with no replacement is true, then the x what y index is in that, we're gonna use it right away, right? The x equal to random dot that range. If it's something already use up, then we're not gonna use that, and we're gonna I think this should be good. All right. All right, and then we're gonna keep track of all these indexes, right? Finally, we also need to keep track of the OOB, right? And then we're gonna do examples. IJ is basically nothing but this one. And Y samples, IJ is this. All right, so now we got this nicely done. Now we can, I think things, okay, I think this one is not correct. This one should be here, all right, because we want to make sure that we have this IDX first. And then once we do that, we append it correctly. Okay, good, things are correct. Now, I'm gonna say that mass equal to np.zeros. This mass is for making sure that I know what should be in the OOB, right? So what I'm gonna do is mass OOB index is equal to true, right? So then I would know that for all of this, they are actually already used. So then what I can do is very simple. That is X samples OOB that append nothing but X mass, right? So I have a tilde here, means that I negate this one, right? So whatever that is not true will be OOB, right? So this is a very nice way to write the code. And then right here we put Y, and here it should be Y, right? And I think I did not make any mistakes. Okay, great. If so, then once we have, so what are we doing here? Well, we're creating examples and Y examples OOB, right? So that is that. So that is the process of, so that is basically nothing but bootstrapping, right? Now we can do the fitting. And we're gonna say that ORB score is equal to 0. And we can print something, of course, out of back score for each tree. All right. And we can now say that for I model and enumerate cell.models. We go to X samples I and Y equal to Y samples I. And then what you do, I'm going to do just a model.fit. And then Y test is np.sArray X samples OOB I, right? And then similarly, we're going to do the same np.s. The reason why we need to do sArray is because we do something like this, and I guess it's in this list. So we do this np.sArray first. Y samples OB, and for that particular I, right? Now we should be able to have everything. Now what do we do is y hat equal to model.predict X test, and then the OOB score is plus equal to accuracy score, Y test comma Y hat. All right, so then we keep track of all this accuracy score, and then finally we're gonna say print tree. Let's say for this particular tree, it's nothing but accuracy score. Y test Y hat. So now you notice that I'm plus equal here. So here is just printing that for that particular tree, right? But finally, after we loop all the trees, we need to say the average OOB score, right? So here I just say that the cell.average OOB score is nothing but OOB score divided by number of trees, right? Which is basically models, the number of models we have, right? And then finally, we just say that, hey, you can do this in any way you want, OOB score, right? All right, and then you can say the print self.avg OOB score, right? So that would give us the validation score. So hopefully things are correct. So let us take a look what we have written, right? So we have init, we have this fit function in which we're bootstrapping and we fit. And then we also have the predict function, right? And finally, we call it random forest, we fit. We should see this thing here. And then when we predict, we should see something. So let us, why not run this line by line, right? Because we want to see everything in actions, right? So let us put things nicely in each line so that we can see things nicely. All right. So, okay, great. So now without further ado, let us restart run all and make sure things should work nicely. Hopefully no errors. Okay, great. So random forest run very fine, but I have something here, right? That is Y samples, and it should not have a column, I'm very sure, right? Because Y doesn't have N. So let me click this one. Okay. And then the clear output restart run all. All right, great. So you can see that once I fit, I can get the validation score, and it seems like mostly some of the score is mostly 0.9, 0.85. So this gives us a rough idea that, hey, if we do the X test, which we set aside, it should get around 93, right? And once we do that, that is the Y hat, we can, we get a pretty good result, that is 1, right? So it's pretty impressive that our model, once assembled, get really high score, right? So yeah, so that is a random forest. So in a nutshell, random forest is basically backing plus out of back evaluation plus selecting random subset of features so that the variance between each of the tree further increase, so that each of the tree produce more meaningful result that can average and give some better results. All right. Thank you very much, and see you in the next tutorial. Bye bye.